So let me just give a quick recap about proton beam therapy. It's like Professor Rankin just mentioned. It actually offers superior dose distributions over conventional X-ray based radiation therapy, and also it's really effective for a wide variety of cases and indications. As to the challenges for protons, so it's really sort of it's very sensitive to setup and range and anatomical variations, so it's not as easy as in X-ray. And also have the interplay effect when we try to deliver pencil beam scanning for a mobile tumor. Also have insufficient high-level treatment outcome data in terms of a phase 3 clinical trial, and also the pencil beam dose calculation algorithm that used in the past many years also is an approximation model. And the last but not certainly not the least is the RBE uncertainty. So, but there's a lot of advances and also mitigation strategy being developed in the last few years to account for this sensitivity to setup and range and anatomical variations. Most of the proton center now we use the robust optimization. So all the uncertainty will be optimized in the treatment plan well in advance. And if there is any change in the beam paths, such as patient loss rate or tumor response and things like that, then we always do adaptive replanting. So the frequency of adaptive replanting in proton is much higher than the photon beam. Well, to deal with this interplay effect, because interplay effect is actually not new in the proton, because if you actually try to deliver like a VMAT or IMRT using the factoring free filter LINET, you actually do have interplay effect. That is the motions of your tumor in relation to your segment. Okay, when you actually deliver 600 MU per minute, the interplay effect is negligible. But if you have a factoring free filter delivery 2,400 MU per minute, then you do have a interplay effect in your clinics. So roughly it's about 5%. We actually have a more randomized clinical trial in proton beam therapy. And for those calculations, we routinely use a Monte Carlo, which has been verified in the last 2 years, well, 2 years ago. And I think I presented this about 2 years ago in this symposium as well. For the RBE, as Professor Rankins already mentioned, we use 1.1. And of course, it's not exactly 1.1 in the Brad Pitt, in the spread of Brad Pitt, but we also have the ability to actually use the variable RBE in our treatment planning system using a research model, and we actually did some study, in terms of calculating using this variable RBE to see what is the impact for those cases. So there's a lot of evolutions in proton. And so this presentation really covers 2 projects that we are currently working on. One is the use of machine learning to improve pencil beam scanning treatment. And the other one is about the flash therapy, which Ramesh has already mentioned. But this is a very hot topic in proton, in particular in the last few months. So how we actually use the machine learning in our QA initially, and also hopefully we can actually improve our treatment plan and delivery. So this is a schematic of the LOSO, which is equivalent to a treatment hat. And you can see that, so it's actually pretty straightforward. You have this IC1 stand for ion chamber number 1, and also you have additional ion chamber IC2 and IC3, they're independent, for redundancy and also for safety as well. And also you have the focusing mallet and also scanning mallet in the X and Y direction. So it's actually relatively simple. And so doing the irradiation of pencil beam scanning beams, so basically the dose information, like spot position, dose per MU, dose per spot, and also the energy are actually stored in this what we call the log file, and we can extract the log file offline. So this is how we actually sort of did it, sort of by initially create a treatment plan in the planning system, and then we export to the we call it verified system Mosaic, and then we actually transfer the treatment bean parameter to our IBA system and deliver the beans, and then we actually can acquire this log file offline using this this open platform called Open Riguri. So totally, we actually look at 30 patients so far, and with that, we actually have 78 pencil beans scanning beans with more than 250,000 spots, with energy ranging from 100 to 226 MeV. So basically, this is the schematic of actually how we actually do it. You basically generate this plans from the treatment planning system, and then we actually extract the log file from the offline, and then we basically go into sort of three different machine learning algorithm, namely the random forest, the neural network, and also the linear regressions. And from that, we actually can first to train a model, and also to have a separate data to test the accuracy of the model as well. And also we look at the mean absolute error as well as the root mean absolute error. Of course, the lower the error, the better the system, right? So basically, you can see that the random forest is a better model for this particular application. So this is the reason why we actually use the random forest to continue in our study. We also develop an in-house software to generate the TPS or treatment planning system compatible DICOM file based on the recorded small parameter from the log file, as well as the predict small parameter output from our random forest machine learning algorithm. And then we can test our predicted machine learning algorithm in terms of dose distribution and also the dose volume histogram against the approved plan. So this, we actually use this prostate patient as an example. On your left is the approved plan. The middle one is the log file delivery. And you can see that there's some degradation in terms of dose distribution. And on your right is the predicted delivery from our machine learning model. It's actually can sort of predict the actual delivery pretty well. And this is the DVH. So the approved plan is in the solid line, and the log file delivery and also the predict delivery are in dash and dotted line as well. So it's just the beginning of our work. So we basically sort of what we want to do is to introduce more training data into our machine learning model to enhance accuracy, and also assess the effects of the delivery error on dose distribution, as well as the accuracy of the model in predicting the delivery dose across multiple patients, as well as different disease sites. And hopefully we can fine-tune the model to further enhance prediction accuracy, and hopefully that we could incorporate this actual delivery uncertainty in our treatment planning as well. So this is the first part, and this is the second part, fresh radiation therapy. So what is fresh radiation therapy? Is basically you need to use an extra high dose rate, as Professor Rankin already mentioned. Even your factory field filter LINET, and it's nowhere high enough, at least 100 times high. And also the treatment duration has to be very short, and also very high dose per fractions. Why we want to do that? Because it really sort of increase the therapeutic ratio of radiation therapy just by increase the dose rate. So, but The challenge now is basically all this work or published work so far is all in electrons, okay? So we have to be a bit more careful, so when we try to use it in proton. So based on the small volumes with electrons, so the dose rate, perhaps you can, see the flash effect at least 30 to 40 gray per second, but very likely you need higher than that, okay? And it's not only the dose rate, it's actually more complicated than that, sort of like you really need to look into the dose per pulse, has to be more than 1.5 grays, and with a few pulses, perhaps less than 10. The dose rate in the pulses has to be higher than the 10 to the power 6 gray per second, and overall time has to be less than 100 millisecond. So far in the preclinical, so FLASH has been used to irradiate cell and 4 animal types. In fact, that one patient has been treated in year 2008, and the result was published just a few months ago. And the effect of FLASH is actually in multiple organ and different animal and one human reproducible, that is the reason why it's so exciting. But it's sort of like it's not as dramatic as sparing all the normal tissue. But it's sort of like I think it's the evidence showing that it's actually improved the sparing of normal tissue by about 30 to 35%. But it's still tremendous, because it really widened this red curve, sort of like from the tumor control probability curve. So how it works? We don't really know, in particular me, sort of like I think very likely is perhaps is the induced O2 depletion in tissues, but maybe also some other mechanism as well. Maybe the oxidation reduction change for normal to dose rate and fresh dose rates are different. Also maybe differences in gene expression as well, and also the circulating lymphocyte may be spared and they generate a T cell, and so we don't exactly really know. It's a big area for research. But one thing that as a physicist that I really need to deal with right now is about dosimetries, how we can measure the dose accurately, how we can measure the dose rate accurately, and also how we can actually calculate the dose accurately. So we are really confident that to solve those challenges. So for dose measurement, we can use the Marcus ion chamber, and also can use the film dosimetry. The Faraday cup can be also used to actually measure the dose rate accurately as well. So just want to review a couple of literature, and this is one actually it's sort of like published last year, done by the group in Switzerland. So they basically they actually report 2 things. One is to use a FLASH and also conventional radiation therapy on 1 millipeg. In addition to that, they actually report their phase 1 single dose escalation trial, delivery dose from 25 to 41 grade on 6 cats with locally advanced SCC of the nasal plenum. So they want to understand the maximum tolerated dose as well as the progression-free survival. Also the endpoint include the depredation and the fibronephrosis of the cat. So this slide Dr. Rangan already showed. So this is basically the treatment planning part of it. So that they irradiate one part with conventional dose rate, the other part with the FLASH dose rate. In fact, the treatment planning was done on the axial treatment planning system. And but anyway, so the FLASH dose rate they believe is about 300 gray per second, and then the conventional dose rate they use about 5 gray per minute. And so they prescribe the dose at 12 mm depth because it's an electron. Okay, so to 28, 31, and 34 gray. So what they have observed that for the part being irradiated with FLASH, so there was depredations about 3 weeks, but the hair follicles preserved it. And whereas for the conventional radiation therapy, they have observed skin fibrosis at 32 weeks after radiation therapy or after the radiation being delivered with 34 grade, and also about 34 weeks with 28 and 31 grade. Okay, so definitely there's a distinction on the pig skin. So what they believe that the fresh radiation therapy over a dose benefit of about 20% for the normal tissues. And as to the cat, so the first cat was treated at a dose level of 25 grade, and then they actually wait for 4 weeks, and then they observe the response from the cat, and then if there's no dose limiting toxicity, then they irradiate the next cat patients with an increased dose, and so on. So the first cat was irradiated at 25 grade, and then 27, 28, 31, 34, and 41. Okay, and then they believe that 41 and then is actually high enough. So what they observed was that the infill depilations start about 3 weeks after fresh radiation therapy, and then with the median follow-up of about 18 months, there's no permanent infill depilations, no other permanent net toxicity or out-of-field side effect. And all the cats have an excellent functional results with no limitation in food uptake or smelling capability. Sounds very good, right? Okay. So, and then for the same group, they actually treat a patients. Very interesting. This is 75 patients with CD30 plus T-cell cutaneous lymphoma. The disease remained disseminated through the whole skin surface, despite the patient have received more than 10 systemic therapy. In addition to that, there were sort of like 110 tumor sites, range from 1 to 5 centimeter size, have need local radiation therapy with a dose prescription of 20 gray in 10 fraction or 21 gray in 6 fractions. Provide good control, but then with high grade of acute skin toxicity. So subsequently, they actually, talk to the patient and then sort of went through all this approval, and then so they deliveries fresh therapy to one of the most symptomatic and progressive lesions on the patient's right forearm. Size is about 3.5 centimeter. So the prescription was 50 gray single fractions, and the treatment was delivered in 90 milliseconds or 10 pulses. And the result was really good. It well tolerated, and the tumor started to shrink about 10 days after treatment, and complete tumor response about 36 days. And after 5 months follow-up, it actually has excellent result. So that actually led to the interest in the proton role. The reason for that is, sort of so far, even that they can deliver, they have a special machine made in Europe, but it's only for electron, very superficial penetration. But for proton, it's a different story, because people said the cyclotron in our facility is a Hoover damped. Basically what happened, that what they mean by that is for our cyclotron to deliver such a high dose rate is relatively easy. I wouldn't say piece of cake, but it's almost like that. So that was the reason why it really generated a lot of interest in the proton role, because we can deliver fresh very easily, okay, from a physics perspective. So basically that's the reason why sort of there's a commercial proton system. So they actually irradiate 400 mice in the East Coast, and this is the way that they did it. They actually delivery 15 grade, 17.5 or 20 grade in single fractions using pencil beam scanning. So what they want to do is basically they irradiate the lung tissues, and they want to look at the response of these healthy tissues, okay, to see what actually the dose-bearing effect on the animal. So the dose rate that they deliver was 40 gray per second. This is the mean dose rate, because pencil beam scanning, you deliver the dose spot by spot in a very fast manner. So, but anyway, so the mean dose rate for the mice to receive the dose was 40 gray per second. And so what they find that is the fraction showing improvement of about 30% in lung fibrosis severity over the conventional dose rate for 17.5 gray. Okay, so how about our system? Okay, so basically from what I understand, with the IBA, because we use the IBA's proton system, it's relatively simple to modify our existing system to deliver the fresh dose rate. That is, we need to insert a new circuit board near the ion chamber 2 and 3. The reason for that is to reduce the saturation effect of such a high dose rate. Okay, and also there is a new configuration in the ScanNoGo. ScanNoGo is the pencil beam scanning control system for IBA. So they just add one additional configuration to deliver fresh. And of course, we have to deliver this high dose rate in the surface mode or standalone mode, and virtually that's it. It's actually relatively simple. And what they sort of believe that the expect dose rate based on the existing maximum beam current at 300 nanoamp, that is our system, sort of can achieve about 200 gray per second for a volume of 2 by 2 by 2. Okay, and if you actually want to irradiate a bigger volume, they believe that they can deliver without any modification of the system to be about 70 gray per second. That is actually also in the in the fresh dose rate. So for IBA, they basically test their delivery at a beam current of 500 nanoamp in France, because in that facility, they actually specifically request a higher dose rate output because they have a designated encoder program there. So of course, the dose rate will be higher, and then so the evaluation of our system in our facility is underway. Hopefully we could actually be able to see the fresh delivery by the end of this year or early next year. So I'd like to thank my colleague and that they contribute to this work, and thank you for your attention.
Thank you.